We have been discussing the special linear group in 2 dimensions, SL2R, and we have discussed how the constraint on the determinant, that is to say AD minus BC is equal to 1, sets the dimension of this group of matrices to 3. Now, when we say dimension of this group, we mean that in a manifold sense. We mean that in the sense of a curved space, a curved 3-dimensional space. Another way to think about it is we have a 3 continuous parameter group of matrices. Now, because the identity matrix is part of the group, we can consider small deviations from the identity in each of these 3 directions. In some sense, these are like tangent vectors at the tangent space to the group manifold at the identity, which is one way to think about it if you like to think geometrically. And in reality, really what this is the Lie algebra of matrices that generate SL2R, which we will also call SL2R, but with some fancy lowercase letters. To study this Lie algebra, the first thing we're going to need to do is look at the structure of how these matrices generate the group. So let M be a member of SL2R that is generated by some matrix in the Lie algebra Q. You might recall from episode 2 that we write this group element as an exponential, so we can write M equal e to the q, or if you like, e to the alpha q, where alpha is some small parameter. There is a relationship between the determinant of the matrix and the trace of that exponentiated matrix, and you can derive this from, it's one of those 19th century mathematicians, Jacobi or Cauchy or Lagrange, or one of those guys, Laplace maybe, I don't know, where they, it's a formula for the derivative of the determinant, and that allows you to derive this relationship. It's fairly intuitive, so I'm just going to take it as a given, but suffice it to say, if the determinant of the matrix M is equal to 1, the trace of the associated matrix in the exponential, say Q, is 0. In other words, traceless matrices generate matrices of determinant 1. In other words, traceless matrices generate SL2R. And that's good because there are precisely 3 linearly independent traceless 2x2 matrices. They're easy enough to identify. Obviously, the matrix with 1 and minus 1 on the diagonal is traceless. So that represents 1. And then the other 2 are just the off-diagonal components. Good. So the Lie algebra is a 3-dimensional vector space, right? We can write them out. I'll leave that as an exercise. Prove that the traceless matrices form a vector space, a 3-dimensional vector space. This 3-dimensional vector space then generates the 3-dimensional group SL2R. Kind of the last thing we need to do then is to determine the Lie bracket for this Lie algebra of traceless matrices. They're matrices, so the Lie bracket we're going to use is the standard one, that is to say commutators. So we just need to figure out what the, if you like, the structure constants are, what the explicit algebraic relationships are. So let's go ahead and name our matrices. So our diagonal traceless matrix, let's call it sigma. And then with our strictly upper triangular matrix, we'll call sigma plus, and our strictly lower triangular matrix, we'll call sigma minus. And then, you can work out. There's lots of different ways to come at this, but why don't we just work through it? The 2 Lie brackets of importance are sigma with sigma plus or minus is equal to plus or minus 2, sigma plus or minus, and sigma plus with sigma minus is equal to sigma. Pretty straightforward. And this, by the way, is going to be an archetype for most of the representations of at least simple Lie algebras. There is so much to say here and so much that I have said in other videos, and we'll put that stuff off for a little bit. Instead, let's look at how these specific generators, these specific Lie algebra matrices, sigmas, if you like, how they generate the macroscopic, the group elements that we discussed last time. So in particular, let's go through those 4 examples that we discussed. So we talked about the trigonometric functions, the rotation matrices. Well, lo and behold, what is the generator of a rotation matrix? Well, that's this linear combination of sigma plus and sigma minus, right? The antisymmetric matrix. So we can plug that into the exponential, and lo and behold, we get back, of course, our rotation matrix. That's one. We can take a different linear combination of sigma plus and sigma minus and find the hyperbolic trigonometric functions, cosh and sinh. Again, very straightforward. Nice, easy to see. These are 2 clear 1-parameter subgroups generated by the Lie algebra. In the third case, for the dilatations, we're going to take sigma that diagonal matrix, notice its plus and minus sign. We can plug that into the exponential, and wow, wouldn't you know it, we've got our dilatations back there too, so that's interesting. And finally, to connect to that upper triangular, what we call the parabolic element, n, we can simply just take sigma plus. Of course, you can do the same thing with sigma minus, and it gives you something that's pretty much exactly the same. Okay, so that concludes our discussion of SL2R, the Lie algebra associated to the Lie group SL2R. That was a warm-up. Now, let's go back and consider the general case. In other words, let's consider the Lie algebra associated to the Lie group of linear symplectomorphisms of phase space. Okay, let's go through that exact same procedure for the linear symplectomorphisms on a higher dimensional phase space. That is to say, the group SP2NR. We've seen that this group is a collection of matrices that satisfies a very specific equation. That is to say, the set of matrices M, such that M transpose JM is equal to J. Now we're going to take that infinitesimal matrix idea seriously, so let's expand out M as something like M equals e to the alpha q, where alpha is an infinitesimal parameter, and so we can write it as M equals approximately the identity matrix plus alpha q plus something order of alpha squared. Plug that into this relationship here. And we see, so the 0th order terms are just j and j, so those cancel out, no big deal. And what we're left with is the first order terms. And that tells us basically that q transpose times j plus j times q is equal to 0. This, in other words, is the matrix condition on the Lie algebra associated to the group of linear symplectomorphisms. So let's block out the matrix in terms of n by n blocks. So let's say q is written as a, b, c, d, right? And so plug that into this new matrix condition and see what we get. Reading off the individual blocks, we find that A, the A block, is related to the D block in such a way that A must equal minus D transpose, and vice versa. D is equal to minus A transpose. Okay, that's one piece of information. Secondly, C and B are both symmetric n by n matrices. C is equal to C transpose, and B is equal to B transpose. So writing this in a way that's kind of like summarizes everything, we've got a new blocked matrix, A, B, C, minus A transpose. And if you think of those blocks as just simple numbers, that is to say, you map back to SP2R or SL2R, you can see immediately that, yeah, this is just the tracelessness condition that we discussed earlier, and that we have 3 linearly independent matrices A, B, and C. And so in particular, for 2n dimensions, we see that this is a generalization of that same structure. Let's do some dimension counting. So B and C are both symmetric matrices, which means that they each contain n times n plus 1 over 2 linearly independent components. And then A and D are in principle just n by n matrices. Those would give us 2n squared contributions, but they're related. They're related by the fact that A is equal to minus D transpose, so that cuts half of those linearly independent directions. And so we just get n squared. So altogether, we have from the 2 diagonal blocks n squared linearly independent directions, and from B and C respectively we have n squared plus n over 2. So in total we find 2n squared plus n linearly independent members of the Lie algebra. Now I'm going to punt the discussion of the explicit Lie bracket till next time, because it's a lot easier to represent it, to demonstrate it in terms of an explicit representation. So we'll wait on that part. But instead, I'd like to describe a few examples of what these matrices were going to look like when we exponentiate them up and into proper group elements, just to kind of poke around and see how the group SP2NR feels. Now that we know the structure of the Lie algebra in terms of these block matrices A, B, C, D, let's look at a few representative examples to kind of give us a tour of how these Lie algebra elements exponentiate up to the full Lie group. So a first and very simple example to consider is the case where the blocks A and D are both 0, but the blocks B and C are related. And not only are they related, we have B is equal to minus C is equal to the identity. In other words, our matrix M, our Lie algebra element M, is given by J, the symplectic matrix itself. What does this correspond to? Looking at the powers of J and how they expand in terms of the exponential, we immediately see the same pattern that we saw with our trigonometric functions when studying SL2R. And indeed, what we're seeing here is this element, J, essentially generates n simultaneous rotations between coordinates and their canonical momentum. And this is hopefully not a surprise. We find n copies of the Lie algebra SL2R inside of SP2NR. And there's a number of exercises that we can base on this. First, I'd encourage you to figure out how to have n independent rotations between the individual coordinates, P's and Q's. You can also look for the n distinct dilatation elements for each of these copies of SL2R, and simultaneously the other SL2R generators, like the hyperbolic trigonometric rotations. Our second example revisits one of the exercises that you've seen previously. Let's consider a Lie algebra element that generates a rotation between two coordinates, say x and y. This would be the case where the symmetric blocks B and C are both 0, and we're looking for a case where A contains within it a copy of the rotation matrix cosine, sine, minus sine, cosine. Armed with that, we know that, and the condition that A is equal to minus D transpose, we know that this forces a similar analogous rotation on the canonical momenta as well. So we can rotate x into y as long as we rotate px into py. So that is interesting. And indeed, it's not hard to see that for SP2NR, we're going to end up with a copy of the rotation groups in n dimensions, right, SON, sitting in there, such that for any time we have one of those matrix elements from a rotation matrix in an arbitrary number of dimensions, we're going to have a complementary copy of that in the D block as well. And you might recall that orthogonal matrices are the matrices that induce rotations, and they satisfy the property that an orthogonal matrix O transpose is equal to O inverse. I should probably say that the orthogonal matrices are in fact grouped elements of the rotation group. And so these would be examples of group members in capital SP2NR. For a third and final class of example, consider the case where the only non-zero block of our Lie algebra element is B. In this case, we can look for powers of the matrix B, and we see that it terminates immediately. In other words, the Lie group element, if we exponentiate such a matrix, would have the identity plus some alpha parameter times B, and that's it. It is a generalization, if you like, of our parabolic element that we studied in SL2R. It's a pretty fun thing to consider. You can physically think of it as a Galilean boost, because in this case, what we're going to be doing is adding to the coordinates some constant factor of the momenta. And the momenta get mapped to themselves. So in reality, it's like a reference frame shift. Of course, there is the dual transformation where we only have a non-zero block C, which does exactly the same thing in reverse. So those are three pretty high-level examples of how the structure of the Lie algebra induces a bunch of interesting transformations that you can think of phase space that preserve the Poisson bracket. Next time, we are going to look at an explicit representation of these transformations, and we'll hopefully give you a clear and concise way to compute the structure constants of the Lie bracket for SP2NR. See you then.